So I think I'm going to go in a different order than I did for the classes yesterday, simply because we're doing two things in a row rather than one thing in a row. So I'm going to do them in a bit of the opposite order, which is I'm going to pull up. Whoops, what just happened there? Control Z. Okay, so so you guys have your timed lab tomorrow, not tomorrow, but on Thursday at 7 o'clock as your second timed lab. It is over heaps and it is over trees. So because I'm doing things in reverse today, I'll talk about the heap section first. You will be provided two Java files, one on trees and one on heaps. The heaps Java file is fairly straightforward. You're going to be implementing a heap. A lot of the hard stuff is already done. There are three formulas that if you've watched the video on heaps, you should know about those three formulas to calculate your left child and your right child, right? And your parent. You know those three formulas, that's worth 10 points apiece if you can implement them. And they're not very hard to implement. And if you forget them, they're in the slides. Then you'll be implementing one of the functions for building a heap. It's not a particularly hard function to implement. The algorithm for doing so is in the slides, right? So you should probably download those slides from Canvas, so you can work on that. Then there are going to be two questions on coding a tree. Those are going to be worth 25 points each. I'll give you the binary tree class, the one you'll be working with tonight, and that one will be. And again, that one will be going over. Two traversal algorithm methods. Now we haven't necessarily done too many of those, so I'm going to rectify that, like right now. Like what kind of questions would you be expected to ask, or expected to be asked? So these kind of questions. This is from my practice exam from last semester. I'll probably put in different questions from my. This question also used to be on the second exam, but this is the type of question I'd give you. You'd be getting on the time lab that it's over trees. So write a method which, given a tree of integers, computes and returns the sum of all the integers stored in the trees. So don't tell me how many nodes are in the tree. Tell me, go through the entire tree, which is made up of integers, and tell me how many numbers are in there. All right. Second is the second one I given as a practice problem is write a method which, given two trees or subtrees, returns whether or not the contents of the entire tree are identical. So in other words, do tree A and tree B, do they store not only the same exact data, but do they store it in the same exact way, right? Is the shape of the trees exactly the same? And they are both solved using the traversal algorithm, right? So there's essentially three types of tree problems, or three types of, there's two algorithms you can use. You can use the zigzag algorithm, which is used for add, remove, contains, and that's fairly straightforward when you're looking for one thing in the tree. If you're doing something over everything in the tree, you use the traversal algorithm. And those two problems are basically 95% of the problems you need to solve. The remaining 5% is if you have to do a breadth first search over the tree and use a queue for that, which is it's the outlier that doesn't use recursion, and we'll tackle that when we get to chapter 10. So not too much of a scare there. So let's go ahead and try going over like a practice problem for the sake of right. Suppose you got this question on right. I give you a tree class and I ask you to implement a method that looks like this. Okay. Public static int number of cars, node string root, right? And my problem is thus: given a tree made up of strings, right? A tree of strings, binary search tree of strings. I want you to tell me the number of basically the number of characters that are the total number of characters that are stored in the tree, right? Not the total number of strings. That would just be the size of the tree, right? But the total number of characters. So in other words, what's that mean? What's that combined? What are we combining there? What attribute of string are we combining? Anyone? Yeah. Yeah, string dot length. So it's just basically the lengths of the strings combined. Right? The number of characters is all the strings combined. So does that sound like a particularly tricky problem? Maybe. But I'm about to show you that it's ridiculously simple to solve. So the first thing we need to figure out is our base case. Now, when you're going through traversal, for your traversal algorithms, remember, your base case is always, am I current, right? You're always making a local decision. And your local decision is, for the base case is, am I at null if root equals null? All right, root is equal null. So let's assume that the root is null. Then how many characters are in root in that case? 0. So we should return 0. Okay, that's the base case done. All right. Otherwise, I am in this situation where I have some word, right? I'll draw it up here. And drawing generally helps if you're confused, right? I have some word stored in here, okay? And then I have a left subtree and a right subtree. And I need to figure out the total number of characters in myself and in my left subtree and my right subtree. Now, one of these is easily solvable. Which one of these is easy to figure out? Yeah? Which one's easy to figure out? How many characters? The root. Yeah, the root. It's very easy to figure out the number of characters I have. Int num cars in root is equal to root dot data dot length. Right? Make sense to everybody? Okay? All right. Now, again, we're in the recursive case here. So figuring out how many... so now let me think about my left subtree. That's a hard problem to figure out how big my left subtree is, right? How big my left subtree is and how many characters are in it. So that means I should solve it using recursion, right? So what do? I say int num cars in left is equal to what? Sorry? It's equal to number of characters root dot left. Okay? All right, any takers for this one? Int number of characters, sorry, num cars in right is equal to what? Yep, number of characters root dot right. Right? Okay, so now we figured out, if I've got all three of those numbers, I figured out how many characters I have, how many characters are in my left, how many characters in my right. So what should I return? Yep, should return I should return num cars in root plus num cars in left plus num cars in right. And that's it. That solves that problem, right? So, and again, this is a completely recursive process, right? Well, how many are in the left side? Well, the left side says, well, I'm not null, so I'll go ahead and I'll take the number of characters that are in my root, right? And figure that out. Then I'll figure out my own left and right length, and they'll do the same until they hit null. Right? Same with my right side. I don't have to really check for null anywhere other than to say, is the root I am currently looking at. Root being not the root of the whole tree, but the root of the tree or the subtree I'm looking at. Right? Every decision here is local. So that looks fairly straightforward, right? By the way, we can get this down to a much shorter statement by just doing this. I will just go ahead and return root.data or root.item. What do we use? Data or item? I forget. Item. Root.item.length plus number of characters root.left plus number of characters root.right. And this is a traversal algorithm. Which traversal algorithm is this, by the way? This pre-order, post-order, or in-order? Which the order? So which one's going for where? Yeah. This is pre-order, right? Because we calculate the root before we do our left, then we do our right. If it was an in-order traversal, we'd do our root in between. Now, obviously, since we're just adding numbers, and you know that's just that the order doesn't matter when we add stuff up. So the order doesn't really matter, but just useful to identify that's a pre-order traversal. Okay, so let's go ahead and now tackle this one, which is also pretty easy. Public static int sumTree node integer root, right? This one says, all right, here's a root. Here's a tree. It has a bunch of numbers in it. All right, I want you to return the sum of all the numbers in the tree. All right, so this is a recursive process. So again, our base case, if root equals null. Okay, what should we do? All right, if our root is null, then if the root of our subtree is null, or the root of our tree is null, then what's the sum of all the numbers in that subtree? 0. That was easy enough. All right. Now let's go ahead and return. Let's just get this down to one line, right? We got to calculate. So again, we're splitting it up into 3 parts. There's the amount of numbers. There's the value of the numbers that I have, or there's the value of the number I have. Then the value of the numbers in my left subtree and the value of the numbers in my right subtree. Okay. So let's do myself first, because it's easy to think of myself first, because this is we're all egocentric here. So root.item, right? That's me. Plus. So how do I calculate the entire? How do I figure out what the sum of all the numbers in my left subtree is? Yep. SumTree. SumTree root.left. Okay. And the last bit? Yep. SumTree root.right. Most questions on the final exam I like questions on the final exam that concern trees. They are almost all around this difficulty. They typically have like one additional step, like literally one additional line to write in there. But otherwise, they're fairly straightforward. Same with the actual exam. But with the final, so in other words, if you can master this format, you've got like on the final exam, you've got 20 points covered pretty much. This is a very easy format. This takes 4 lines of code, albeit a bit of a long line, right? But this is a traversal algorithm, right? I figure out, I handle the center, I handle the left, and I handle the right. All right, so this one is a bit of a harder one because it involves 2, right? We're dealing with 2 things, right? So this is the last one I'll go over. All right. So here we're trying to figure out are 2 trees equal. So this one's a bit trickier because we've got a bunch of other things that we don't have one base case, we have a bunch of base cases, right? So let's go ahead and think of this. Well, how would we know if so because there's a bunch of possibilities here, right? Not just one. Here there was 2 possibilities. Root was null or root wasn't null, right? Here we have tree A can be null, tree B can be null, tree A might be null, tree A is not null and tree B is not null. So we've got we've got 4 possible combinations where basically both are null, both have a value, one has a value but the other is null, one has one has a value but the other is null, right? Everybody see how there's 4 different combinations? Fortunately, only 3 of those are base cases and 1 of those is a recursive case. So let's just simply code up those if statements. So if tree A is null and tree B is null, right? That's case 1. Okay, and then I'm going to use the power of copying and pasting, right? All right, otherwise maybe what if tree A isn't null but tree B is, but what if tree A is null but tree B isn't, right? Right, these are both symmetric cases over here. And then we'll just put an else over here because in that case, well, otherwise they're both not null, so that's the default. That's the only possibility left. Everybody kind of understand those? These are the 4 combinations you can have, okay? And if we want to be super specific, right, these are all independent, right? They can only one of these can happen. So if tree A is null and tree B is null, let's think about that. If tree A is null and tree B is null, are they equal? Yeah. So we're going to return what? Return true. Okay? Makes sense to everybody? If they're both null, right? And this is a much harder question than I'd actually ask. This is why I put it on the practice exam. Again, this sum tree, this one over here, the sum tree one, actually comes from an actual final exam that I've given out, right? This is one that I've given in a final. Okay? So, equals. If tree A is null and tree B is null, then they're return true. They're both the same. If one is null but the other isn't, right? Then they're most certainly not the same, right? So return false, right? Right. If one is true and the other is, sorry, if one exists and the other doesn't, right? Then they're not the same. They don't have the same shape. So we'll return false for both of them, right? It's just easier to lay them out as the 4 individual clauses rather than trying to stack these together and make it and overcomplicate it for ourselves. Always keep it simple when you can, because we're not really built for doing logic. We're built for getting frustrated and getting angry. So, better to keep things simple so we don't have to work so hard on it. All right. Otherwise, well, now we do have something. Okay, that's a bit. So now they both have something, okay? So they both have something. So we know that essentially we're in this scenario, right? We have here, right? We've got tree A over here. We've got tree B over here. And we make all our decisions locally. So the only local decision we can make is are the values we both have the same? I can't figure out about our respective left and right locally. We'll have to recursively solve that. But locally, I can check, is the value in root A the same as the value in root B? Right? That makes sense to everybody? So, else, if tree A dot item dot equals tree B dot item, well, then we'll have to do some recursion there. But if they don't equal, else we'll just return false. Right? Right? If they equal each other, then we've got to do some problem solving there. Otherwise, so if they equal, we have to do recursive checking. But if they don't equal, right? If the item, if I've got if it's a tree of integers, for example, and I've got an 8 here and a 7 here, right? Then the trees are obviously not the same, right? But on the other hand, if we've got a 7 here and a 7 here, then I've got to figure out, okay, do my left trees match and do my right trees match? Okay. And that's, yes?
Where does this other matching test for equivalence?
It just did right here in this if statement. It's checking, are the two items equal in the root. And now we're going to check in this if statement, we're going to check, are the values in here? Sorry, not are the values are the same, but are the left subtrees and the right subtrees the same? Yeah.
Was the definition of the two trees being equal that?
It's not enough. So I've tried to specify that it's not enough for us to just do an in order traversal, right? Was that what you're thinking of?
I was thinking like if they weren't like balanced, if they were the same.
Right. Right, so what I'm specifying two trees being equal as they have to have the same exact structure. When one zigs, the other zigs. When one zags, the other zags. Right, they have to have the same shape as well. They have to store the exact same data in the exact same way. Otherwise, otherwise you can solve it by just saying, oh, you can just do a pre-order traversal, and it doesn't, we don't go through the exercise of what I wanted to do. Yep. So now we just have to, so here actually we can do this in one line as we can. But I'll split it up into 3 for simplicity. Okay? I'll create a Boolean over here that will figure out are the left same. Then I'll create a Boolean over here to figure out are the right side same. Okay? And then I'll return left same and right same. I don't have to check if the center is same because I just did that over here. I don't have to check if the root is same because I just did that in the if statement. If the root isn't same, then I'm just going to just return false. I'm not going to bother checking my left subtree and my right subtree. That would be a waste of time. I can just kind of short circuit and immediately return false if those aren't the same. So to figure out if my left subtrees are the same, I just simply type equals tree A dot left and tree B dot left. Right? Because if they're the same shape, then this will go over the same subtrees, right? And then for the right same, I just do it with the right. That makes sense to everybody? So even though these problems look like they're complex, this one was about as complex as it gets, but all the cases, they're pretty easy to figure out if we stop and think about it. Yes?
What would happen if instead of just doing tree A dot left, we did tree A dot left dot item?
Then it wouldn't allow it because the item because it'd be looking for a node, not an item. Right. We're passing in a node here, and if we only just went and compared the left item, then obviously it wouldn't necessarily detect anything lower, right? If we were just checking tree A dot left dot item and tree B dot left dot item, assuming we could pass it in, then that would only go one layer, and that wouldn't check any of left's children, so the recursion would stop at that point, and that wouldn't necessarily be what we want. We only want the recursion to stop when there's nothing left. Okay, this one's way more difficult, way more involved than the one I would give on the exam. Sorry, on the exam and on the this one would be way more difficult than the one I would give on the timed lab. Now on the exam, as I'll go over when we get closer to there. So the exam, by the way, when is the exam? Excellent question for those of you thinking about that. So it's not next week, right? Woohoo, right? It'll be on the 8th for you guys, 8th of November, right? So 2 weeks from now, so week 11, right? And the reason for that is I feel like what we'll be able to do is it lines up very well with producing the content. It's because next week you're going to be covering next week is all about using how to use hash tables. And it's less important that you guys know how to build one from scratch. More important that you guys know how to deal with collisions. Less important that you know how to build one from scratch, though. And as you'll see, building one from scratch is actually conceptually pretty easy, and then it's just a bit of ugly things that you have to do inside. It's actually the idea is actually laughably stupid, as I say during my videos. But you'll be able to get hash tables done. And one of the things that I found during our final exam is that a lot of the more difficult problems we've had, or problems that students find difficult, they can be solved in a couple of lines by simply using a set or a map appropriately. So learning where to use those is pretty good. Now, going back to what I was saying, as far as the difficulty of questions for trees you'd expect on the exam, there's a particularly fun question I actually like to ask on that exam. And it'd be difficult if I just handed it to you, but I instead break it up into multiple parts, with each part being independent of each other. And so that way you've got a problem that's fairly easy and straightforward for you guys to solve. But anyway, these are the type of questions that you would want to ask yourself. So if you need to do some practice on yourself, I'd maybe practice printing out all this. Like I'd practice, here's a tree of made up of strings. Let's print them all out let's write a function that prints out everything in pre-order or post-order or in order, right? Let's write a method that, rather than printing them all out, returns all the strings, right? A single string that holds all the values, right? Then maybe do that for integers, right? Do something that basically that does selective. Maybe add only the even. Maybe sum up only the even items, right? That adds a bit of a twist that might be that you might see on an exam or something. So, make sense? Those kind of questions. So, but basically, these questions are when you're doing something over all the items. The code eventually ends up looking like this, right? And it's fairly straightforward. You've got your base case. What if the thing is null? I guarantee you're only getting one argument for the timed lab, by the way. So when you have two things for the timed lab, it looks like this generally. So, but sorry, if you have two things for this, it would be messier. But you're only getting problems which would take one tree, because that makes sense. This one was just simply to demonstrate the same principle. Okay. All right. So with that, we have an in-class exercise today, so I'll start up a new video for that.